Every time you ask an AI chatbot to rephrase an email or draft a line of code, you trigger a massive physical chain reaction. That single prompt flashes across subsea fiber cables at the speed of light and hits a $10 billion fortress that draws more power than a city of 250,000 people. We treat AI like software magic floating in the cloud. But AI isn't software, it is the most aggressive infrastructure project in human history. I am Marcio. I invented the first data center management system back in 1995, and most recently I served as a senior director of technology at Google. Let's dive in. Today we are tracing your prompt backwards through the physical world, from the screen in your hand through the silicon straight into the global power grid. Because right now the entire tech industry is locked in a silent hardware war, the bottleneck isn't smart algorithms anymore. The bottleneck is physical reality. Part 1. How autocomplete became AI. Before we look at the physical hardware, we have to unpack what an AI chatbot actually is, because it isn't what most people think. Artificial intelligence isn't new. Nearly 30 years ago, IBM's Deep Blue beat world chess champion Garry Kasparov. But specialized software like chess engines is an artificial general intelligence. They can think outside their narrow rules. So, how did we get from playing chess to systems that can pass the bar exam? It started with modern autocomplete. When you type a search into your browser and it predicts the next word, that's a statistical language model. If you type blue, it calculates a high probability for the next word being sky, dress, or whale. A few years ago, researchers tried an experiment. What happens if you feed a language model the entire internet and throw massive supercomputers at it? Instead of just predicting the next word, the model began building an internal map of human concepts. It stopped just copying syntax and started reasoning through ideas. Some critics call LLMs a glorified parrot, just repeating what humans wrote online. But frankly, a lot of human learning works exactly the same way. Here is how that process works in practice when you type a prompt. An LLM can't read English directly. It breaks your text into bite-sized chunks called tokens. On average, one word equals roughly 1.25 tokens. Your words are then converted into numerical IDs, fed into the model, and processed to predict the most logical response. When AI companies charge developers per token, they are simply billing for the math required to process those numerical chunks. And every single one of those math operations require physical energy, physical cooling, and specialized silicon. Part 2. Inside the $10 billion fortress. Now your prompt has left your phone, flashed through thousands of miles of fiber, and arrived at its destination, the data center. A traditional data center is essentially a massive warehouse packed with standard servers. Think a 20,000 square foot facility drawing enough power for about 4,000 homes. Then came big tech hyperscale data centers. These giant campuses can span 5 times the size of a Walmart supercenter and draw as much electricity as a mid-sized city. But AI changed the game entirely. Standard computer chips are built for general tasks. AI models need the specialized hardware originally designed for video games, Graphic Processing Units or GPUs. Because GPUs process thousands of tiny mathematical operations simultaneously, they turn out to be the perfect engine for neural networks. That single hardware shift transformed NVIDIA from a game chip manufacturer into the most valuable company on earth. Here's the catch. GPUs run blistering hot and devour insane amounts of power. To keep up, tech giants are pouring nearly $1 trillion a year into a brand new breed of AI-optimized mega data centers. These facilities are a completely different species. A single state-of-the-art AI data center campus can stretch across 150 football fields, consume enough electricity to require its own dedicated nuclear reactor, and cost up to $10 billion to build. This is why tech leaders are now floating wild ideas like data centers in space, recommissioning nuclear power plants, and fighting over regional power grids just to keep up with your daily prompts. Part 3. Why should you care? Having led engineering and product teams through the 90s dot-com boom, the mobile revolution, and the transition to cloud, I've seen this exact pattern before. In the late 1990s, telecom companies laid millions of miles of optical fiber underground. Then the market crashed. Critics called it a reckless bubble, but that overbuilt fiber network became the physical backbone that enabled Netflix, YouTube, cloud computing, and the entire smartphone economy a decade later. We are watching history repeat itself. Right now, we are building the computing foundation for the next 50 years. Whether current AI software is overhyped in the short term or not, the physical infrastructure, the high-density power grids, liquid cooling systems, custom silicon, and subsea fiber is of permanent value. And if you are building a career today, here is your unfair advantage. Stop treating technology like a magic black box. The highest paid, highest leverage professionals over the next decade won't be typing prompts or writing basic application code. They'll be the ones who master full stack reality, how software collides with hardware, and how thermal limits constrain algorithms, how data latency dictates design, and how energy costs govern business economics. Conclusion and call to action. Understanding these deep systems is how you future-proof your career. If you want to dive deeper into building a high-leverage career as an engineer, founder, or tech leader, check out the content in the channel. If you got value from this teardown, hit subscribe and drop a comment with your take on the AI Power Grid bottleneck. And I'll see you in the next episode of Careerscast.